Hello everyone, welcome to the third lecture of the second chapter. In this lecture, we're going to talk about graphical solutions to solve for speciation in an acid-base reaction. So for this particular lecture, we're trying to construct PC-pH diagram first, and then try to solve the solution pH based on the constructed diagram, and also later expand it for a polyprotic acid solution. So the first two parts, we're going to focus on just a monoprotic acid, and then later on, we're just expanding, like finding a logical way to expand it for further diprotic or triprotic acids. So just a quick overview of what we talked about before. So we talked about an acid reaction as a reaction that releases proton eventually, so A minus plus H plus. Then we quantitatively described this using the acid dissociation constant, which was basically the activity of A minus proton divided by the protonated version of the acid, which is HA. And we saw that most of the time, because the concentration are pretty low, we can basically use the concentration terms rather than the activity to make it a bit simple. So then in the second lecture, in the previous lecture, actually, we talked about speciation. So the unique entities that we have in an acid-base system. For example, in this case, in this particular case, this reaction, we mentioned that when we talk of speciation, we always have H plus and water and OH minus coming from water. And now by introducing this reaction, we're actually introducing A minus as well, and also HA. So using some algebra or algebraic solution, what we talked about in the previous section, we basically did N species. If we have N species, then we need N equations. And then when we use some mathematical operations in order to solve this. And most of the time it was a non-linear equation. So we could solve it using, like, let's say a software or just using some mathematical operation in order to get either an exact solution, or we could use some assumption in order to simplify this non-linear equation, for example, a quadratic equation, to just a linear equation. And we use several assumptions, which are all, they carry physical intuition. So this assumption, for example, we mentioned for strong acid, we assume complete dissociation. So for example, if this HA was a strong acid, for example, HCl, so this HA concentration would be negligible. Or for example, when we mention we add acid, then the OH minus concentration is almost zero. But as you saw in some of the examples in the previous lecture, we have to double check all the assumption that we're making after we finish the calculation. So this is the key. If we're assuming something, we have to go back to check that assumption. So in the previous lecture, we used algebra basically to solve the equations for this N equation that was driven for N species. So N species means N unknowns, N concentrations to be known. So we need an independent equation. And this equation we drove from mass balance, charge balance, and also some equilibrium constant. But now we want to use graphs in order to figure out speciation at, for example, a given pH. So what would be the pH? What would be the speciation? That means concentration of all the individual species if we are, for example, at a pH of 4 for an acid-base system. So this is, as I mentioned before, this is the key information for any environmental system, to know what are the species and what are their concentration or their contribution. And then later on, because these unique entities, these unique species have like different properties, so we can, by understanding their concentration or their contribution, we can approach the system differently. The clear example was that disinfectant, HOCl, OCl minus, they have a different strength in terms of disinfection. So if we have a tool to evaluate their concentration at different pH, it would be very beneficial to know how effective the disinfectant is at that condition. So we used algebra before, but now we want to use graphs. So graphical approaches to chemical equilibrium problems are useful because they provide a visual representation. So as any other graphs, so they are visual. We can visually look at it and just, they provide very fast, rapid information. So the other thing is, most of the time, constructing this these graphs for an acid-base solution is pretty fast. Sometimes by just doing a rough back of the envelope calculations, we can have like a general sketch for a system. And that would be very fast compared to using algebra, what we talked about in the previous lecture. So that means there's a big advantage for using graphical solutions to figure out about speciation of a given acid-base reaction. So going forward with be more specific on the types of graphs that we are looking for in this lecture. There's actually one very known plot that we often use in this lecture and in the field of like graphical solution for acid-base system in general. And that's the PC-pH graph. Or as the book says, it's a log C pH graph. So basically in one hand, we have the concentration as a function of pH. So long story short. But instead of concentration itself, we're using the P term, P of concentration, as we did for proton, translating that to the pH of the solution. So basically what we have for PC is basically the same as pH. It would be minus log of the concentration of C. Just a very quick example. For example, if the concentration of sodium plus is 10 to the minus 3, then PNA would be 3. Just to give you an idea of like this P function, mathematical description of P function. So if we have that, we have this sort of graph. In one hand, we have PC for all the species. And then in the x-axis, we have pH. So basically what it says is how, for example, the different species concentration changes at different pH. So again, very valuable information. We had this a little bit in some of the previous lecture. For example, we had this alpha term. We saw that this HOCl, it's changing like this, and then OCl minus is changing like that. But this is a more general term for within graphical solution for acid-base systems. So this PC term as a function of pH. So as I mentioned, the textbook uses log C. So basically we're using PC. So that means these values in our book are just negative. So the graph you see in the textbook is basically 0, minus 2, minus 4, minus 6, minus 8, and so on. But here we're basically using just the positive value, or the opposite value, because we're using minus log of C as opposed to just log C. Just keep in mind, this graph is basically reversed. So as we go down, the magnitude of values increases. So Just keep in mind, if you're looking for a slope that is positive, in this representation, that slope would be negative. So let's just focus on the simplest scenario, which is basically water. Let's construct a PC pH plot for pure water. So if we look at water, we know that just if we look at the species, we have only H plus and OH minus. And also let's consider the ideal scenario. So just not use activity, just rather use concentration. And we also, based on the equilibrium, we know that Kw is equal to the concentration, or to be more accurate, the activity, but here we use concentration, of OH times H plus, which at 25 degrees C, this would be 10 to the minus 14. So here we have these values as a function, not as a function of P, but represented using P. So let's just do minus log of both sides of this cell, this equation. So we get minus log H plus OH minus is equal to minus log of 10 to the minus 14. Or just expand this log using mathematical rules. So this is actually this part. Using a log rules from general mathematics, we can expand it as minus log H plus minus log OH minus is equal to 40. So what we see here is this term is pH, and this term with the negative sign would be POH. So pH plus POH is equal to 40. So now we have a line for POH. So POH is basically 14 minus pH. So if we look at this graph, POH, so just imagine OH is our C, because we mentioned this C is basically for all the species. So now we want to just drive one line for OH. Every species has a line here. So H line for H, it should be linear. We basically pH versus pH would be just a linear line. And keep in mind, this is reverse. So the line for H would be just a simple line with a slope of 1, but in this case, because the representation is this way, is minus 1 in this particular graph, if you want to look at it as a normal graph. So this would be H plus, representing H plus, and the slope would be 1. So here we saw that this would be the graph for the line representing OH minus. So the best way, I would say, is always to have like 2 dots, 2 points, and then draw the line there. First of all, the line has the slope of minus 1. So the slope for OH line would be minus 1. So that means in this graph, it would be like that, or like that, or like that. And then the interception with the x-axis is actually 14. So basically, all of this line which have the slope of minus 1, the interception of only this line has the satisfy this equation. Or sometimes to just have points. So if we are at pH 14 here, then the pOH must be 0. So this line. If we are pH 0, then the pOH value should be 14. So basically, the OH line should be like that. Okay, the slope is -1, and this represents OH. Or in this graph, it represents pOH. And then this point, at some point that the concentration of H plus and OH minus are the same, which is basically the equilibrium, or at pH 7, which represents the equilibrium at 25 degrees C. So two things. One is every single species has a line here. And the second thing is these lines are linear because we're eventually dealing with a linear equation because we use this P operational P terms. So it makes everything linear. And the other thing is these intersections of two lines are very informative. We're going to use it later, but just keep in mind in this case was just pH 7 equilibrium, or where this pH was equal to pOH. Just pOH, just put pH here, and then it's going to be at 7. So as we mentioned, OH minus and H plus present in every aquatic system. So basically, no matter what system we're looking at, we always have these two lines. If we're adding acid, if we're adding base, either strong or weak, we always have these two. So for any system that we're going to drive, we cannot skip this two. And having this two later, you'll see that it gives us very important information about the pH of the solution. For example, by just looking at the intersection of appropriate lines. So we'll see that in a minute. But just keep in mind these two lines, one is representing H plus and the other one is representing OH minus. So now let's plot this PCPH for a weak acid in pure water. Basically the previous scenario, but we're adding an additional weak acid to the system. But the logic would be the same. So we're using P function, and also we're trying to simplify as much as we could and to get to that sort of linear equation that is informative and it's simple enough to work with. So in this case, in this particular example, we're actually looking at propionic acid, something that we looked at in the previous lecture, but using algebra. We approached this using algebra, and then following by a few assumptions, we tried to make it as simple as we could. So going from like a polynomial equation to quadratic equation and then to a linear equation. So that was using assumption, and then the core was algebra. But here we have the same solution, 10 to the minus molar, 10 to the minus 3 molar HPR, propionic acid, added to pure water, and then obviously it has the same pKa. But now we want to use the graph in order to evaluate the system at different pH or calculate the pH when we add this much to the system. So the first part, we're going to just construct the PC-pH plot, and then in the second part, we're trying to adapt information in order to calculate the pH of the system. So looking at the acid reaction, so this is basically HPR, a weak acid, dissociating to PR minus plus H plus, and then the Ka would be the concentration of PR, again using concentration, not activities, because we consider that as an ideal solution for the sake of simplicity, and HPR. So when we look at, we can rearrange this Ka term. So let's just rearrange it a little bit. Then we get PR minus H plus equal to Ka H PR. So what we're trying to do is to come up with an equation that we can apply that P function in order to get to a linear equation. So now we apply that P function, or minus log of both sides. So it's going to be minus log of PR minus H plus equal to minus log of Ka times HPR, or just expanding this using the same rules we follow in the previous example. So then this would be minus log of PR minus log of H plus is equal to minus log of Ka minus log of HPR. Or as we define this P terms, basically this is P PR plus PH, so this is small letter p, is equal to PKA plus PHPR. So this would be the core line for all the mathematical operation we have, all the lines that we're going to have in a PC pH diagram. So this would be the line. Now our job would be to simplify this line as much as we could. So that would be the task. Just keep in mind, one thing is that the total PR based on the mass balance would be just PR plus HPR. Just keep that in mind. So now let's see how we can simplify this logically in order to get to individual lines for either PR, HPR, and also for OH and H plus, which is the same in every system. So the first thing is always to consider this as at different conditions. So let's say we have, so let's go to the graph. Let's see what information we can get out from the question to help us a little bit on this particular example. So the question tells us that the total concentration of PR would be 10 to the minus 3 mole. So this is given by the system. So that means when we look at the graph, always the maximum, the upper limit for the concentration of PR or HPR would be 10 to the minus 3, or minus log of 10 to the minus 3 would be 3. So this PC, we can mark it here, so 3. So the max, those two lines, we're not considering the trend yet, the max they could get for PR and HPR would be this line, with this much, given by the system. The other information that we're always interested, because that's very informative, is the pKa. For this particular system, pKa is 4.87. So let's mark also 4.87 on the x-axis. So something like here. So this could be also something that we might need it. So the total concentration, and we mark these two as the pKa. It's basically this line we're considering. So now let's see how we can simplify this line that is true for all the species. So the first, let's see if pH is equal to pKa. So we're basically picking one point on the x-axis, and that point is equal to pKa, what we just marked. So in that case, we showed that before, that at pH equal to pKa, the concentration of species are basically equal. So, or if you put it inside this equation, so these two will go out. So what we end up having is PPR is equal to PHPR. So that means the individual concentration are the same. So what we get here is, for example, for PR is equal to half of the total PR, right? The concentration is the same, so it's going to be just the half of what we originally had at this point, at the point that pH is equal to pKa. So let's do the p function on this one, because that might be informative, because we're dealing with the p functions. So if we do p function, PR is equal to P total PR plus, because we're doing minus log, so this would be minus log of 2, or P total PR plus log of 2 is 0.3. And then this would be the same for PHPR. But what does it mean? Like, what does it mean that, what are we doing here for this particular example? So what we showed here was that at this point, the point that was marked on the x-axis, the concentration are the same. So these two lines, whatever lines that represent PR and HOPR, then they intersect, so they cross each other, and then that cross point would be P total only moved by 0.3, so increased by 0.3. So let's go back to the graph. So basically, if this is the total, we're talking about also this particular pH. Then these values are 3.3. So it's moved by 0.3 here. So we have this 1.4, or slightly moving towards the left. This would be here. So this is where PR line and HPR line would cross at the pKa. So pKa. But now let's see how it would change at pH that is moved a little bit to the left or to the right. So let's see how the trend would change if we go either this way or this way. So let's just use an arbitrary point of pH moving 1 unit compared to pKa. So again, 1 unit is just an arbitrary. This could be 1 unit going to the right, that means increasing pH, or 1 unit going to the left, decreasing pH. So, but we just want to see the sensitivity of the system. So let's put this into the core equation. So then this would be basically PPR plus 1 equal to PHPR, or this means Okay, let's just move this a little bit. We need more space probably here. So this means PR divided by HPR would be 10, or would be, 10 to the power of 1, 10. So this is just a simple mathematical operation to get from here to here. Basically, you bring HPR here, so this would be PPR minus PHPR is equal to -1. So then you just have the operation of PR divided by HPR, and then P, and then just doing reverse of log, then you get to this point. So what this says is basically if we move 1 unit towards the right side of the pKa on x-axis, then the concentration of PR would be 10 times more than the concentration of PR. So it would be fair to consider PR is almost total PR. If we do the same thing for going 1 unit to the left, so this would be, then this ratio would be 1/10, because we're dealing with a -1. In the log word, that means 1/10. So that means if we go 1 unit to the left of the pKa on the x-axis, then the concentration of HPR is 10 times more than PR, or it's almost the concentration of the total. So what we do is basically going back to the graph. So this was the first point we figured out. Now if we move 1 unit to the right side, then the concentration reaches the total concentration. So then let's say 1 unit would be almost here. And of course, as we increase this term, or going more to the right side, then what happens is this ratio is getting bigger and bigger and bigger. So then this would be more true as we go to the right side. So basically what happens is as we continue to going to the right side, this would stay the same. So then we have this point, and then following by a line, following by just so this would be for PR. And now we have the same thing if we go left with the HO or HPR. So I'm going to use a different color for HPR. So then 1 unit to the left, so this would be here. This would be HPR. So this represents HPR. And this represents PR. Okay, so now the question is, how does it change from here to this side for PR, and how does it change from here to this side at higher value for pH for HPR? So that's the second question. Or if we go back, this would be the third condition, or other pH values. So at other pH values, let's just look at just PR, because this would be the same logic for also HPR. Then here, when we look at the equation, then we get PPR plus pH equal to pKa plus pHPR. But the point here is we can actually simplify this equation based on what we just observed in the graph. So now we're talking about a lower pH than this value. So we want to see how this blue line would change after we pass this. So after we pass this, the concentration of HPR is almost equal. So it's not changing as a function of pH. As we saw, it's almost, it's pretty much equal to the total concentration, or this was the total concentration. So if we look back to the graph, to the equation, then we see that this is not changing. This is also a constant. So these two are constant. So that means we can simplify this by saying PPR is equal to a constant minus pH. So what it tells is that we have a line that the slope is -1. And we already have 1 point of that line at pKa. So by knowing 1 point and the slope, mathematically, we can draw the line. When we don't really care about that constant because we have that point. So what it says here is basically the rest of this graph, the slope would be -1, which using this representation, that means the slope would be 1, the positive slope. So the way it goes, it's something like that. So this is the complete trend for PR as a function of pH. As I mentioned, the same logic we can apply in order to get to HPR. So just assume this is 0.1 or -1, the slope. So this is the slope for HPR. So we simplify this to the point, then the slope for this one is -1. We had 1 point, so we were able to construct the graph based on that, and the same logic for HPR. And as I mentioned, we always have the lines for water. So basically the OH line and the pH line would be always, and the H plus line would be always there. So OH minus H plus, then HPR and PR. So this is basically the graphical representation of all the species as a function of pH. So quickly we can tell, for example, if the pH is 10, then this would be the concentration of H plus, the concentration of HPR, the concentration of OH minus, and the concentration of PR. So very, very informative. So this is true based on the mass balance and based on the equilibrium. We consider mass balance, we consider equilibrium. But we actually didn't consider charge balance, or we didn't answer this question that if we add 10 to the -3 of the total, what would be the pH? Where is the pH in this graph? So that's sort of not an information that is readily available for this graph. So it's not as informative as just picking a point along an x-axis, finding a pH. So to find a pH, we need some logical approach to use this graph to find a pH for this particular concentration that are given. For example, 10 to the minus 3 for this sort of acid system with this pKa. So the only equation that we didn't use here was the charge balance equation. And when we add 10 to the minus 3 molar HPR, eventually when we reach equilibrium, it has to satisfy, the charge balance has to be satisfied. So charge balance, if we write it, considering all the species, positively charged species, H plus is equal to negatively charged species, which is PR minus plus OH minus. So generally speaking, when this is satisfied, we are at equilibrium, or this has to be satisfied for this given system. So we use that and this graph to find the pH. So how? Let's define two terms. The right-hand side, or just the left-hand side, which is basically the left-hand side of the charge balance. In this case, is H plus. And also let's define the right-hand side. In this case, this would be PR minus plus OH minus. Right? Just the left-hand side, the right-hand side of this particular charge balance for this particular system. So mathematically speaking, when the charge balance is satisfied, that means the left-hand side is equal to the right-hand side. Graphically speaking, that means if we construct LHS and RHS, the point that they cross, that's where the left-hand side is equal to the right-hand side. So then that means we need to construct left-hand side and right-hand side on this graph. So that would be the task. And the intersection of that graph, those two lines, would be basically the pH. It would basically satisfy that, and that pH would be the pH of the system. So left-hand side is pretty simple. It's basically the H plus line. So this would be the H plus line. And then this would be the H plus line. So this was also, oh, sorry, this is OH minus line. So this we should need to H plus line. So this would be also the left-hand side. But now the question is, how do we construct right-hand side, which is basically PR minus and OH minus, the combination of two, when we have only PR line and OH minus line? So since we're dealing with the P function, we can basically drive a mathematical logic how to combine these two. So this is one line, sorry, and this is the other line. We can have like a mathematical logic in order to figure out what is, for example, the combination of these two lines in P graph, in a P-type graph. But to make it simple, we can just simply assume the P line, which is the simplification actually is very accurate. This P line follows the bigger value. So we want to combine this line, and then as we trace across the x-axis, we follow the bigger line. So the higher value. So the right hand side goes like this. At this point, this value is bigger and bigger and bigger than this line. So the combination would also follow that. So this would be following because PR is bigger. But now we get to this point. At this point, the OH line is bigger. So the combination is follow like the bigger value. So this would be our right hand side of the charge balance. Or if you want to be more accurate, this graph follows like something like this. So there's a tiny difference here, which is basically 0.03. You can do the math and then figure out about that. But I would say if you want to combine two lines in a P graph, then just go with the higher value. Or the value that is higher, in terms of in this particular representation. So whatever is on the top. Yeah, whatever is absolutely on the top. And now we have these two graphs. We have RHS, we have LHS. So we just need to see where they cross. And that's this point of the cross. Almost, the pH is almost 4. So this would be the system pH. Or LHS and RHS cross at pH of almost 4. And if you remember from the exact solution, without even assumption, the exact solution from the previous lecture, this was, pH was 3.96 based on the exact solution. So this means this graphical solution is pretty accurate also, but the biggest benefit is not the accuracy. The biggest benefit is first, it's fast to construct this. I mean, don't consider the very first example to represent constructing the PC-pH graph, because we spend a lot of time talking about the logic, talking about why we need these two lines and those sort of things. But eventually, it's very, very fast. You just need pKa and the total, and then just follow the line. And then these lines for a monoprotic acid, the slope, as we saw, is basically 1. So all the slopes that you're dealing with here is either 1 or -1, or they're flat. So, and then just the charge balance logic tells you the LHS should be equal to RHS, and then this is where you find the actual pH for that given concentration of the weak acid, in this case 10 to the -3. So if you add 10 to the -3 molar HPR to the solution, the pH would be 4. And then as you adjust the pH, this would be the speciation, because you can just trace the line across a given x-axis, which is basically the pH of the solution. So now moving forward, we have like a similar example, but working on the disinfectant that we talked about several times throughout this lecture. So see how we can construct it this time a little bit faster. So a few things we need is, first of all, what would be the total? So just mark it. This is 10 to the -4. So this would be 4 on this graph. So this would be the total. And then 7.5 is the pKa. So 7.5. And this would be here. Yeah, 7.5. So we know at this point And this point, the species, let's just first talk about the species that we have. H plus, so we need a line for that. OH minus, HOCl, and OCl minus. So these are our species, and we need to figure out about the individual lines. So starting from basically the H plus, OH minus, and the H plus, so OH minus, H plus. Then we can focus on HOCl, the protonated version. We know that at this 7.5 and the total, we just need to, so this is 7.5 and the total, come down 0.3. This would be somewhere like here. And then to the left, we have HOCl. And then to the right, we have the OCl minus. And then after this point, they just follow the line for -1 or 1, the slope of -1 or 1. This would be the slope for OCl minus. And then I'm using one color for both of them here, just you know which one is which. Yeah. So this would be OCl minus, HOCl. So now let's look at, so this is, as I mentioned, this is very fast. Now you have the plot. Basically, that's it. The question is now, what is the pH for this given condition? And then we rely on charge balance in order to find the left-hand side and the right-hand side. Similar to the previous case, the charge balance is basically H plus is equal to OH minus plus OCl minus. Or the left side left-hand side, sorry. So the left-hand side is equal to H plus. The right-hand side is equal to the combination of two lines, and as we talked, the line that is at bigger value, which in this case, in this representation of the graph, is the higher value. Okay, so now we have the left-hand side basically the same as H plus. So this would be our left-hand side, and then the other one is just OH and OCl minus. As you can see here, first OCl minus is bigger. Then we get to this point, and then OH minus. If you want to be more accurate, here is like this. A little bit, as I mentioned, 0.3, just curves a little bit. And that's because of the log function. So this would be also our left-hand side, right-hand side, and then they cross right here. And this would be the solution pH. Of the solution. So pH would be almost equal to 6. So what I want to highlight here is basically this system was, or this method was way faster than the previous system because it's just constructing a few lines, and then based on the charge balance logic and the LHS, RHS, and how we combine the lines in this P curve, we can quickly tell what's the pH. So that's the most one of the important output from this graph, but the other output was basically also knowing the speciation as a function of pH. So pretty quick, right? But in these two examples, we didn't add any other ions to the system. So always the left-hand side was proton. So it was relatively simple to figuring out about like these lines. It was relatively simple to figure out about the pH. But now we want to make it slightly more tricky, slightly, not much, by just changing the HPR this time to NaPr, so sodium propanate, if I'm not mistaken, but NPR, we're adding it. So we're introducing another type of ion to the system. So now here we have the same thing for constructing the graph, but we need one more line also for sodium. So species would be H plus, OH minus, sodium, PR minus, and HPR. So we have one more line. To quickly proceed, we have this OH minus line, the H plus line, the pKa value was for this system was 4.87, so 4.87 is here, pKa, and the total is 10 to the minus 3, so this would be 3. So if we come down here, 0.3 and 0.3, then we just need to draw the graphs. This would be like that. This. Then for HPR, then the PR minus to the minus 1, and the other one also with the slope of 1. Okay, now we also have sodium, which shouldn't be that difficult. It's basically sodium line. Sodium is not involved, so the concentration of sodium based on the speciation is always equal to the concentration of total sodium, which in this case is also 10 to the minus 3. So the sodium line would be always this dashed line that I'm constructing, which I think you don't see it. Yeah, it's dashed line. It's basically constant. So this part would be PR minus. This line is also, or let's just put it the other side, PR minus. This is always sodium. The sodium line is just like that. And this is the HPR. And we have the usual lines for OH minus and the H plus. Okay, so the first part was pretty simple, as we did before, just considering the total concentration and also the the pKa for the system, which is 4.87 here. But now let's drive the charge balance to see what is the left-hand side and the right-hand side. So let's see. So in this system, the charge balance is basically the positive charge, sodium plus hydrogen, equal to PR minus plus OH minus. So what we have here is that the left-hand side, now this time, it's also a combination of two lines. Plus hydrogen, and the right-hand side is equal to PR minus plus OH minus. So we can follow the previous logic and actually draw this left-hand side, right-hand side, figuring out where they cross. And then we know how to combine two species to get to the second line. So it's something that we practiced in the previous two examples. So let's draw the left-hand side, tracing the sodium line versus the proton line. So the one that is bigger. So if we start from the left part of the graph, so here we see proton is bigger, and then proton goes down, but sodium is bigger. So you see the logic. This would be something. Then this would go here. So let's call this the left-hand side. And then we do the same thing for the right-hand side. As we have the individual lines, PR, we just need to combine PR with OH minus. Okay, PR is bigger here on the left-hand side. And then we overlap here, and then the OH. Oops, should I? So this would be our right-hand side. But as you see, there's a problem here. And the problem is lack of resolution. So we did right. We mentioned that whenever LHS is crossing RHS, that's the pH of the solution. But now, all of these points are, it seems, all of this point, LHS is almost equal to RHS. Because we don't have that accuracy to pinpoint the exact equivalent of these two, might be something like this. We don't have the accuracy to pinpoint that exact cross between these two lines because we're just relying on the number that was bigger. We're just assuming that. But then in reality, it's slightly bigger than this, and the trend is changing. We're lacking the accuracy here. So we don't know where the pH is in this zone, but it is there. The logic using this LHS and RHS is true. But in this case, it doesn't have a good resolution. So what happened in this example compared to the previous example? The only difference was we have a combination on both LHS and RHS, right? And then that means we had to combine two lines for both. And then this adds, this reduces the resolution. So if we somehow make this LHS or RHS just as a function of one species, then we're dealing with a line that is an approximate and dealing with a line that is exact. So it's way easier to pinpoint the cross, for example, if it's here or it's here, rather than just two lines that are overlapping. And overlapping considering our poor resolution. Otherwise, they don't overlap at several points. They just overlap at one point, for example. So let's twist the charge balance and see how we can make either of these guys as a function of just one unit. So let's revisit the mass balance. So mass balance is telling me the concentration of total sodium. It's basically the concentration of sodium. And also, this value is the same as the total concentration of PR. So this would be the total concentration of PR. Because we're adding 10 to the minus 3 NaPRs, that means 10 to the minus 3 Na and 10 to the minus 3 total PR, right? So then this would be equal to HPR plus PR minus. So now let's substitute this equation into the charge balance. So sodium, so we'll revisit the charge balance. So when we get to, instead of sodium, HPR plus PR minus plus H plus is equal to PR minus plus OH minus. Simplification. So then you see our LHS, let's call it LHS revisited, or just, revisited would be HPR plus H plus, and then our RHS revisited would be only OH minus. So what we did was defining different lines of LHS and RHS. This time one of them is just one species or one line, the other one is the combination. So by doing this simple trick, we actually simplify this. This makes sense. This is another representation of charge balance. But we're taking advantage of different combination of lines that we have here in order to get to the point that is within this range. So we shouldn't get some result, for example, in this range, because this was telling us the exact pH of the solution, but the resolution was not good. But that means we're still dealing with this range. So now let's draw the revisited LHS and RHS. So to go with LHS, it's basically HPR and H plus line. So this would be HPR. This would be the H plus line. So that means the LHS would be this time, I'm using green, whatever is bigger, and that is here H is bigger, then HPR is bigger, then HPR is bigger. Or one more time. The first part, HPR, the H plus is bigger. Now the HPR is bigger. So see, this is HPR, and this is H plus. So now this is bigger, and then continue with HPR being bigger. So this is revisited LHS. And now the revisited RHS is basically the OH line. would be this line. This is RHS revisited. And they cross at this point the pH of the system, which is around 7 point, let's say, 8. So this would give us pH of 7.8. So here, as you see, this is within this range, but this time it's just 1 point of cross, which makes it very accurate and easily readable compared to this range of the original LHS versus RHS. And if we look at the actual number, we see that the pH is around 7.9. So pretty accurate for this sort of graphical solutions. So what we observed was retwisting. So this LHS, RHS are not written on the stone. We can just basically play with them to basically find a condition that satisfies the charge balance overall. It could be the original charge balance or it could be a revisited charge balance. But the trick is always go for LHS and RHS that one of them has basically only one term. So here one term, here two terms, but in the previous original case, 2 terms versus 2 terms. So that's why you see you don't have that much of the overlap, that much of the accuracy, that much of the resolution. But it was right, but you can not easily get this value out of this. So, but we revisit it in a way that using a mass balance, eventually get to these 2 lines that are crossing at only 1 point. Always keep in mind, you get the bigger value when you are tracing the, if you want to combine 2 lines in this P graph. So, pretty straightforward. I guess we should be like very fast on graphing the very original lines. And then after that, basically, and these are the original lines still, and based on the given condition, what you're supposed to do is basically draw LHS, RHS, and then find the cross point. If it's, and just make it in a way that you have only one term, either in LHS or RHS, so it would be easier to find the exact point rather than just the range. Okay, just a quick note on like constructing the graph, not just finding the pH. This is about constructing the graph. So we talked about monoprotic acid. We didn't talk about, for example, a diprotic or in general polyprotic acid. So, but here we can mathematically drive the logical approach, how, for example, the slope is changing as we proceed, as we pass, let's say, a pKa or something like that, like what we did for a monoprotic acid. But here we just use the same rule, which actually tells a lot about the system. The simple rule is a simplification of a long mathematical derivation. And that simple rule says, if for a multi, or even for a monoprotic acid, when you cross a pKa, when you have a line, when you cross pKa, then the slope changes by 1. So if there's another slope, then it just by this. And the opposite if you go from here. If there's a pKa, the slope goes, it's -1, and then another pKa, the slope is -2. So again, that -1 that we drove was logical. It was because PC, the equation, the term behind pH was either 1 or -1. But now here, as you pass another pKa, that means you're combining 2 reactions. That means you're combining 2 terms of pH. So the slope is either -2 or +2. And if you pass that to another pKa, then the slope would be -3 or +3. So that's the very easy way to quickly construct the PCPH diagram for uh, a more than one proton acid, so polyprotonic acid. So here we just want to do it for carbonic acid, 10 to the minus 2. So the same thing as we did before. So 10 to the minus 2, that means the PC, the total would be 2. So this is the total. And then the pKa values, the first one is 6.3. Say here. And then the next one is 10.3. So here. So we have this hidden lines. So we start from the left. It goes by at the lower pH, the most protonated version, which makes sense. You have more H plus here than here. So it makes sense if you have more H2SO3 than no H species, which is CO3 2 minus here. So we start from H2CO3. As we proceed, it's almost identical to the total. So then 0.3 here. Then that goes by. Let me first draw the lines for OH and H plus, because that helps us to have like a better understanding of slope of 1 on minus 1. So this would be OH and H plus. So now the slope should be in parallel. So we pass the first pKa. So pKa 1, pKa 2. So the first one, the slope would be parallel to, or the slope would be 1. It should be something like this. And now we pass another one. So the slope would be 2. So roughly 10, 12. Yeah, something like this. So this would be our bicarbonate. This would be H, or this would be carbonic acid itself. Now the next line is the one related to the second one. So let's just first write this reaction. Maybe that helps. H2CO3 going to HCO3 minus plus H plus. This is pKa1, and then HCO3 minus going to CO3 minus 2 plus HPKa2. So here we have the next species is HCO3 minus, this one. So basically we have between the pKa and pKa2. And either way, when we pass pKa, the slope here goes to minus 1. And on the other side, we just pass 1 pKa, then the slope is again changed by 1, not 2. Okay. So this would be our bicarbonate, HCO3 minus. The other species, the last species, we have this one, which is basically starting from the very left side of the graph, passing 1 pKa, then the slope changes by 1, and now another pKa, so the slope changes now by another 1 unit, so -2. So this would be the CO3 2-. This would be for OH- and proton. So finding the exact solution using this graph would be a little bit tricky. We might go through that in the problem solving session, but this is the logical way to construct the graph. So right now you have basically all the information on how to calculate the speciation at a different pH. Let's say your solution is at pH of 7, then the major composition of your species would be HCO3-, following by H2CO3, following by a CO3 2-. So the CO3 2- is 10 to the minus almost 6. This is 10 to the minus 3, and this is almost 10 to the minus 2 at that pH. So this is really informative on how the speciation works as a function of pH for a wide range of pH for all the species, all in one graph. So here again, the finding the pH would be a bit difficult, a bit more tricky, not difficult, a bit more tricky than RHS, LHS. Defining those, it's a little bit more trickier here than just the normal monoprotic acid system. But it's doable. We might, as I mentioned, we might do it in the problem solving session. But the point here was, as you cross pKa, another pKa, the slope changes by 1. So if it was, let's say, a phosphoric acid, you would be something like this. Or this was a bit exaggerated. Something like this. And as you pass pKa, the change in slope is increasing or decreasing by unit of 1. So we learn how to construct the PC-pH graph in this lecture, and we basically solve the solution for the pH of the solution for a monoprotic acid. And also we expand this logical way of constructing these lines for a polyprotic acid, such as a bicarbonic acid that we did at the end. So what you need to do, as I mentioned in the lecture, is just basically you go for PC-pH graphs, and it's basically a combination of lines, a combination of like individual lines for individual species. And we define this LHS, left-hand side and right-hand side term, driven from charge balance, in order to find the pH of the solution. And also just keep in mind this LHS, RHS might be a bit complicated in terms of like having the number of terms in each. So we assume it's better to have in either of them, in one of them, just one term. For example, in either RHS or LHS, just one term, just which represent basically one line. And graphically speaking, where they cross is the pH of that particular solution. For more readings, I refer you to these chapters in the book. More examples are provided. And in the next lecture, we're going to talk about computer-aided solutions. So another way to basically look at the speciation, what we were targeting for the previous lecture, this lecture, and also the following lecture. What would be the concentration or the contribution of each species at different pH? Or if we want to change the pH from one value to another value, how much of a particular substance we need to add to the system. So, yeah, thank you so much and have a good one.